Oh man, if you thought we were going to stop graphing at sine and cosine, you were absolutely incorrect. We got tangent, cotangent, secant, and cosecant functions to graph. I'm pumped. We're going to start with tangent, and what we're going to use is the unit circle to think about this tangent graph and relate it to that to see what's going on here. Because oftentimes we know what numbers to plug in and how to shift things around, move them up and down, and stretch them and all that stuff, but we don't really think about like where it came from and connect it to other parts of trigonometry. So let's do that. All right. So first off, I know that my ordered pairs here are cosine of theta, comma, sine of theta. And I know that tangent, as a review of our unit circle, is equal to sine of theta over cosine of theta, right? It's our y over x. While we often refer to tangent as slope, changing y over changing x, y over x, sine over cosine. Awesome. Wonderful. All right. Well, let's see here. I'm thinking my quadrantals are going to be some important points. You know, that seems logical. So let's see what happens at each quadrantal, shall we? So I've got x and y. Now at 0 degrees, let's see here, that's going to be y over x, so 0 over 1 is 0. Then at pi over 2, I have y over x would be 1 over 0. That's undefined. I can't divide by 0. And then at pi, I've got 0 over negative 1. Again, that's going to be 0. And then at 3 pi over 2, I'm going to have negative 1 over 0. Again, I can't divide by 0, so it's undefined. And then I'm going to have, back at 2 pi, I'm just going to be at 0 again, right? Because that's the same as 0. So I've got this pattern going on of 0, undefined, 0, undefined, 0. Well, what happens when it's undefined, right? That's either going to be like a whole or an asymptote if we think about like rationals. It's going to be an asymptote here because we're dividing by 0 there. Nothing's canceling out like in rationals where we get a whole. This is going to be an asymptote. So how about I graph a couple of asymptotes here? We're going to go at pi over 2, as I said. Lovely, lovely. So I'm going to change the color here. I'm going to go with, how about a light green for my asymptote? So we've got an asymptote there. And then I've got another asymptote at negative pi over 2. Oop, not negative pi. We said 3 pi over 2. Okay. But if I did go, think about like a negative rotation, that would put me at 3 pi over 2, right? So if I go negative rotation of pi over 2, negative pi over 2, that's equivalent. That's a coterminal angle to 3 pi over 2, so it should behave the same. So I would have an asymptote there. I was just jumping ahead. I see the future sometimes. And then again, this is going to be a coterminal to that, so I can put an asymptote there. And as what we see is this pattern's repeating itself. It is a periodic function, right? It's going to periodically repeat itself, right? Okay, awesome. Fantastic. So I got these asymptotes. So clearly there's something going on between them. How about I pick some values? I'm going to focus on that center area, this one right here, to pick some values, right? Those are some nice teacher brackets, weren't they? Okay. So now let's get some in between. And I'll go with, you know what? I'm not going to do blue. I'm going to go back to, I'm going to go with a lighter blue. No, I'm going to go with purple again. I'm just going to go back to it. All right. So if I'm staying between pi over 2 and negative pi over 2, I'm looking at this portion of the unit circle, right? Negative pi over 2 is that angle of rotation down to a positive 3 pi over 2. Okay, so what would be some convenient values? Well, if you look at the blue ones there, if I'm going to be dividing, this is going to be inconvenient, but hey, look at the red one here, the one that's a pi over 4. Those are the same. So anything divided by itself is just 1, right? So at pi over 4, which conveniently is right here. And if this is 1, 2, 3, well, pi over 4, comma 1. And then if we look at our negative pi over 4 rotation, which is this one right here, that's going to be a negative divided by a positive. So that's going to be negative 1, which would be right here, negative 1. Negative 2, so on and so forth. Okay, and at 0, we did say it was going to be 0 according to my ordered pairs. And if we were to continue to plug in values closer and closer, what we would see is that it's going to be behaving in a way that it's going to be going towards positive infinity over here and negative infinity over here to make this kind of S shape. It kind of reminds you of almost like a cubic function in a way. It's not, but it kind of has that somewhat similar shape. Okay, so, well, if we continue doing this, I know that pi, we already said it was 0, right? And then if I look at my, after pi here, I'm going to have it's going to go to positive right here. And when it's at 3 pi over 4, it's going to go negative, right? Because I have one negative. The other one I have two negatives. So again, it's going to have the same pattern right here and here. And it's going to be doing this all day long, right? And in here, I'm going to see again. We're running out of room. But I'm going to see the same thing repeating itself over and over because, whoops, it is a periodic function. All right, so again, you've seen tangent, but you may have forgotten like how we actually build it, why it is the way it is, why it has those values, right? Why does it look like that? What's going on here? And it's easy to forget some of the general shapes. So whenever I'm at a loss, I often just start plugging in points and think about that. I'm like, hey, well, why don't I just plug in some points? Okay, if I don't know what the heck's going on, at least I can plug some in, see if I can evaluate it, and get a general picture going, right? We don't have to memorize what every single graph looks like. The more we use them, we just kind of remember them, but you don't have to memorize everything. So speaking of our periodic functions, perhaps we should figure out what the period is. Now, with sine and cosine, our period was 2 pi. That's how often it repeated itself. But as we see here, this is happening more frequent. In fact, it's happening over from negative pi over 2 to pi over 2. That's just pi. Okay? And now my domain is actually different here. So what we have to restrict some values in this case, whereas like in sine and cosine, it just kept going, right? But here we got these asymptotes that we have to exclude. So if I'm going to write my domain, I need to think about, well, what can x not equal? Well, it can't equal negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, so on and so forth. But am I going to write everything out? No, there is a convenient way of going about that. And I'm going to write it in set builder notation, x such that x cannot equal. We'll start with how about pi over 2, which is our first positive, pi over 2 plus, and how often is that happening, right? How often are we repeating ourselves? And that would be every pi, right? That's its period. So plus pi n or n pi, however you want to write it, but I'm going to write it with pi n. There we go. Okay, so starting at pi over 2, and then I'm adding pi each time. And if n is a negative, then I'm subtracting pi, so I am still taking care of the other side of the graph, right? Awesome, fantastic, wonderful. Now my range are my y values. Does it ever stop going up and down? No, it doesn't. So in this case, this is all real numbers. And I guess since we already did set builder, I'll continue in that same fashion. Y equals all real numbers, or you could write it as, negative infinity to infinity, right? Depends on what it's asking for. Cool. Awesome. Fantastic. Wonderful. That's tangent. All right. Now for cosecant. Cosecant is our reciprocal of sine, right? So this is equal to 1 over sine. So in my math brain here, I'm thinking maybe some of those critical points, those wonderful, convenient, awesome values, of sine could possibly be helpful, right? So what I'm going to do is in a lighter color, again, and I'm going to go with light green. Light blue this time. Let's change it up. I'm going to graph my sine function, okay? So my sine function, and I should probably label the y-axis there. All right, we're good. So for my sine function, it starts at 0, 0. And then at pi over 2, it's 1, right? That's my first quadrantal. And then back at pi, I'm at 0, and then over here, I'm at -1, so on and so forth. Awesome sauce. Let me go back the other way. Oops, skipped one. I think I did that one other time too. My goodness. Can't be skipping. Okay, so we can see that sine curve, right? Now, let's think about what's going on here. So again, it's the reciprocal. So perhaps we can find some points where we're like, hey man, that doesn't make sense, okay? Or there's something weird going on there. How about at every spot where it equals 0, right? So 0 is like 0 over some number, 0 over 1, 0 over 2, or 0 over some number, we'll call it n, right? Well, if I do the reciprocal of that, now it's n divided by 0. Can I divide by 0? No. What happens when I'm dividing by 0 on a graph? We're going to have asymptotes. So now what I'm going to do is I'm going to pop some asymptotes in everywhere it equals 0. All right, so now what I have are these asymptotes here, because if it's equal to 0 and I do the reciprocal, it's undefined, so there's going to be an asymptote. And now what's going to happen here is if I were to plug in some numbers that were closer to those asymptotes, what I'd start to see is that I'd get this wonderful U-shaped looking thing going on here in each one of these spots. If you properly did that Desmos activity, you would have seen this as well. But there we go. We've got our wonderful cosecant graph. It's the reciprocal of sine. Now, let's start talking about the period, okay? Well, for our period, how often does it repeat itself? We can see it happening in, like making a cycle here, right? So it has the same period, in fact, as our sine function, which is 2 pi. That's how often it repeats itself. The asymptotes come into play with the domain, right? So once again, we could say x such that x equals, we could just say 0 plus, let's see here, n pi, or pi n, right? Every pi, we have an asymptote. X cannot equal, how about pi n? That way, if I plug in 0, I get 0 for my asymptote. So it can't equal 0. It can't equal pi when I plug in 1. When I plug in 2, I get 2 pi, right? There we go. Awesome. Fantastic. Last thing will be my range here. So for my range, let's think about what's happening here. And if I'm going to, stay in our set builder notation, I'm going to have y such that y is, let's see here, less than or equal to -1, and y is, we'll go with or, I'll just put a comma. Y is greater than or equal to +1. There we go. Right? There's that little gap there. Cool. Awesome. Fantastic. Wonderful. You could also have written that as like ∞ to -1 with a bracket on the -1, right? ∞ to -1, and then +1 to +∞. Lovely. All right, now on to secant. All right, I'm going to go through this one a little quicker. We know that secant is our reciprocal of cosine. So it's 1 divided by cosine of x. And I'm going to put those little ghost points as we often talk about them. So my points for cosine, I'm going to pop those on the graph real quick. And boom, there we have them, right? We got that cosine wave going. And now, wherever it equals 0, that's where my asymptotes go, right? Because I can't do the reciprocal of that. It'd be 1 over 0. That's undefined. All right, so we have our asymptotes in place there. Speaking of reciprocal, has anyone made the reciprocal TikTok that I was talking about in the last? No, okay. Well, if you do, please send it. All right, so same kind of idea here. We're going to make those wonderful looking U's like we did before, but found those other points that are not on the asymptote. And boom, there we have it. Wonderful, beautiful secant graph. Alrighty, so period. Once again, it repeats itself every 2 pi, just like the cosine graph does. Now for my domain, again, I'll use set builder notation, x such that x does not equal, well, let's pick one of the asymptotes. How about pi over 2? So pi over 2, and how often do those asymptotes occur? They occur every pi. They're spaced out every pi. So plus pi n for some number, some integer n. There we go. And then my range. My range is the same thing as my cosecant graph. And there we have it. Wonderful stuff. Last one, cotangent. All right, for this one, I did bring back our wonderful friend, Mr. Unit Circle. Let's start with our quadrantal, shall we? Shall we? All right. So for at 1, 0. Well, now cotangent. Hold up. Cotangent of x is equal to then cosine of x divided by sine of x, right? Let's remember that. It's the reciprocal. There's the dance. Reciprocal of tangent, right? So those are flipped around. So now it's going to be x divided by y. So 1 divided by 0, it's undefined here at 0. And then when it's 0 divided by 1, that's just 0. And then here it's going to be undefined. And then here it's going to be 0. So it's a slightly different looking starting spot for our pattern, right? Well, let me pop some asymptotes in. So I went ahead and actually graphed a few more asymptotes than what we originally saw. We saw them at 0 and pi, but I can go ahead and continue around, and then at 2 pi, I'm going to have an asymptote. And if I go negative, a negative pi, and negative 2 pi, I'm going to have those asymptotes as well. All right, cool. Well, now at pi over 2, we saw that it was 0, so I know that I'm going to have the point of 0. I'm going to go green now. It's going to be 0 here, and then at 3 pi over 2, it was 0 again, and I can also go that negative rotation there and there. Okay, so we're starting to think, hey, man, this is kind of looking like tangent just shifted a bit. Well, let's think about this for a sec. At pi over 4, which is right here, right? At pi over 4, it's going to be positive 1. Boom. And I just scaled it a little bit there. And then at 3 pi over 4, if I look at that, I'm over right here. Well, it's a negative divided by a positive, so that's going to be a negative 1, because right, they're the same, right? Anything divided by itself is 1, but it's going to be negative in this case. So I've got this same kind of shape going on that I did before, but it's like reflected kind of, right? So same kind of tangent shape, just it looks reflected. And we can repeat that in each little section there. Awesome sauce. There we go. Now let's go ahead and get our period. Well, our period, how often is it repeating itself? Well, 0 to pi, pi to 2 pi. So every pi, just like tangent, it's going to repeat itself every pi. How about my domain? Well, my domain, once again, it has an asymptote at 0, so x can't equal 0. And then also every pi, it's no bueno, right? So we can write it in its simplest way would be x cannot equal pi times some integer n. So that could be a positive integer, a negative. It could be 0, right? That would take care of that 0, x equals 0 asymptote. Awesome. And then my range, well, my range is all real numbers. Y such that y equals, oops, not equals, all real numbers. Close the bracket. Boom. Wonderful. Nice. All 4 of them. So now we're going to do a couple examples where we got some crazier stuff going on. Let's do it. All right, so we've got ourselves a cosecant. Oh, this one looks just terrible. 3 cosecant of 3 pi over 2 x. Well, first off, let's remember this. Cosecant is our reciprocal function of sine, right? So let's plot out those ghost values, some people call them whatever, of our sine function, right? So how about we find our period? Okay, so normally it'd be 2 pi, and I'm going to do 2 pi divided by that guy right there. So 2 pi divided by 3 pi over 2 is the same as 2 pi divided by, multiplied by the reciprocal, right? 2 over 3 pi. And if it helps, you can throw a 1 over there. So my pi's cancel, and I end up with, we got 4 thirds. All right, 4 thirds. That's a terrible 3. That's a little better. Now, how am I going to scale this out? Well, remember we got 4 chunks of our sine function until it repeats. So let's divide 4 thirds by 4, which would give me, would be the same as multiplying by 1/4, right? So I'm going to get 4 over 12 then, if I divide this by 4. And then I can simplify that down to 1/3. So each one of these are going to be 1/3, 2/3, 3/3, which is 1, and then 4 thirds. And look at that. I cut it into 4 chunks. 4 thirds is my period. There we go. Okay. And I can go back the other direction too if I'd like. Negative 1/3, negative 2/3, negative 1, and negative 4 thirds. I'm going to go ahead and stop there. Enough graphing, 2 periods, right? So now it's time to put in my sine points, but actually first, you know what? I should probably scale this out. 1, 2, 3. And negative 1, negative 2, negative 3. Okay, cool. So let's plot some of those points, shall we? For our sine function, I'll do that in light green. For our sine function, I start at 0, then I pop up, and I come back down to that midline. And then I'm down to the negative value. There we go, to negative 3, and then I'm back up. And I can repeat that over here on this side as well. Cool. There's my sine. I could see that, the sinusoidal function. But I'm going to have some asymptotes, aren't I? Ooh, look at that, almost perfect spot. So at those 0 spots, right, because the reciprocal of 0 would be undefined, as we said, I'm going to have an asymptote there. And then I'm going to have an asymptote here. All right, there we go. We got our asymptotes. And then we know that it has that U shape where it's going to be going up and down based on where it's at. So I'll go dark green for that. So I'm going to have boom, boom. There we go. There we go. And wonderful. So I actually have 2 periods of this function right here, right? I've shown 2 periods. It's repeating itself twice. All right. Now my domain for this, so there's no shift or anything like that. So we know that it's x such that x cannot equal. Well, it starts at 0, so and then it repeats itself every, in this case, 2/3. And if you had 2/3 again, you get to 4/3, right? So 2 over 3n would be my domain for this one. Can't equal that. And I would be able to get to each value there based on putting a -1, -2, a 0, so on and so forth, right? And then my range, well, my range is going to be y such that y is less than or equal to -3 and y is greater than or equal to +3. Not too bad, right? Not too terrible. So we find that period. We divided it by 4 to get our sections, and that helps us scale out the graph when we're dealing with a nasty period of a trigonometric function, right? Cool. That was fun. Now, some of you might be like, hey, like, what's the amplitude of this thing? The sine function has an amplitude of 3, but our reciprocals do not have an amplitude because it goes up to infinity and beyond, right? So there's no cap as to how high it goes, so it does not actually have an amplitude. Great question, kids. I'm glad you raised your hand and asked that. All right, it's time for some secant graphing. So that is our reciprocal of cosine. So we're going to think about this as a cosine function first, and then we'll graph accordingly. All right. So first off, I do need to deal with that that period there, that period multiplier of 4. Well, if I take 2 pi, I divide it by 4, that gives me pi over 2, right? So that's my period. Awesome. Wonderful. Now I'm going to take that period and I'm going to cut it into 4 chunks to scale up my graph, right? So pi over 2 divided by 4. Actually, I probably shouldn't write that there because it's not equal to 2 pi over 4. So pi over 2 divided by 4 is pi divided by 8. So I'm going to go by pi over 8. It's pi divided by 8. And 2 pi divided by 8 is going to be pi divided by 4. And then I'll have 3 pi over 8, and then 4 pi over 8 is just pi divided by 2. And boom, I've made it through the period, right? And I can go back the other way too. Cool. And now I see some other stuff going on. I want to make sure that I scale that y-axis accordingly. I see that 5 out in front, so the amplitude of my cosine function would be 5, and I also have a vertical shift of 2. So that means I need to go as high as probably 7 or a little bit more because I'm dealing with the secant function, which doesn't have an amplitude, remember, but the cosine does, which we're using to graph this. So I'm going to scale up to maybe, how about like 8 or so. All right, so there we have it. I decided not to mark the negatives just because it gets a little bit messy sometimes. Okay, so let's go ahead and start graphing our cosine function. Now, one thing to mention, or our cosine points, one thing to think about is our midline is going to be at 2, right? So let's think about that as we're graphing. I'm going to do this. I'm going to do this as a solid line for the purpose of erasing it, because I don't want it to look like an asymptote either, right? Our dashed lines are our asymptotes. So I'm going to erase that at the end. It'll be easier to erase it that way. So there's my my midline that I'm dealing with. Now for a for a cosine function, I'd be starting now 5 above, right? So 5 above would be at 7. And then I'd come back to my midline, and then I'd go 5 below it. So I'd be at 3. And then I'd come back to my midline, and then I'd be above it 5, so I'd be right up about here. And now I'm going to get the other part too. All right, so we have our points for a cosine function. Now we can use that to graph our secant, which is its reciprocal. I'm going to throw in some asymptotes where it's on the midline, right? If this wasn't shifted up by 2, a vertical shift of 2, that would be on the x-axis. It'd be equaling 0. We'd know, hey, that's undefined. Well, the same thing's going to occur here. I've just shifted the graph up. Okay. So let's see here. We got an asymptote here. I've got an asymptote here. And there we go. So I got all my asymptotes in place, and now I can go ahead and graph Maybe I'll use a little different color just so it's a little more distinct. I can graph my my secant function. So it's going to be heading up for the first part. It's a weird arrow, and then down. All right, there we go. So we actually have here, it looks like 1, 2.5 repeats here, periods that I've graphed here, right? So we got, 2.5 periods graphed of this graph. And now let's talk about our domain. Well, our domain, let's see, our asymptotes. That's what we got to look at, right? Because those are my excluded x values, or my theta values here in this case. All right, we got to be careful with that. We're using theta this time. I hope I didn't mess up the last one. We were using x. Okay, cool. Woo, got worried. All right. So our domain is theta such that theta cannot equal, and it would be, let's say pi over 8 would be our first value we'll use, pi divided by 8 plus, now, how often are those occurring there? It's 2 pi over 8 to get to 3 pi over 8, right? I have to add 2 pi over 8, so every pi over 4. So pi divided by 4n. There's my domain. Theta cannot equal that. Okay, I'll get an asymptote every time. My range, we can use y because it's y equals y such that y is less than, and it was less than or equal to -3. I am including those values. And then greater than or equal to, and it was 7 is where we started. Again, not terrible if you break it down by its reciprocal function, plot some of those points, and then what I like to do is I'm going to go ahead and take away, there it is, take away that midline. Lovely, lovely. Got my nice asymptotes there. Good stuff. Nice, clean, precise graph. Sort of precise? All right. Let's keep going. All righty. So we got another tangent graph. This time, though, we have a period multiplier in there that we have to deal with. So let's think about what's our period of tangent. Normally, it would be pi. So we do pi divided by pi. Give me a little squiggle there. Over 4. So it's the same as pi multiplied by 4 over pi. Feel free to throw that over a 1 if it makes you feel warm and fuzzy inside. So the pi's cancel, and I'm left with 4. Okay, so my period is 4. And you know, that's actually real nice, because if I divide that by 4, I'm going to end up getting 1, 2, a 3, a 4, so on and so forth, right? Nice and easy scaling on this one. How wonderful. How fantastic. I don't know how to count. I'm just putting a 4 there. Cool. All righty. So we've got our graph scaled out, right? I think now it's time to actually, graph this. And if you forgot like the general pattern of tangent, that pattern is usually where it's like we start at that origin there and you go 2 of our scalings out, and that's where your asymptotes are. But sometimes it's easy for that to slip your mind. But let's think about it for a sec. If I were to plug in 1, as I know this is one of my important points here, I get pi over 4. And I know at pi over 4, tangent is equal to a positive 1. So I'm going to throw a little scaling here. Okay, and if I plugged in 2, I'd get 2 pi over 4, which is pi over 2. Ooh. Pi over 2, that's where tangent would be 1 divided by 0, which is undefined. That's where my asymptote goes. All right, let's put an asymptote in. And I'll change colors for that asymptote. Okay. So it's starting to take shape. Now, what about the other direction there as I'm thinking about my general behavior here? Well, if I plug in 0, tangent of 0 is 0. And if I plugged in -1, I'd get negative pi over 4, which I know my unit circle would give me a -1 value. So that would be right here. And then again at -2, I'm going to have an asymptote. All right. Well, I can clearly see what's going on here with my tangent function based on what I know and the few points that I plotted here. There's 1 period of my tangent function, and if we'd like, we could do a little bit more here. All right, I did 1 more. We got 2 periods of our tangent function. That looks pretty dope. I'm going to leave it at that. No more time needed to be taken there. So what's my domain here? My domain. I have an asymptote at 2, so let's go with, and we're dealing with theta such that theta cannot equal 2 plus, how often does it repeat itself there? I've got 3, 4, 5, 6 is where so every 4, so plus 4 n, right? That is my period, so that makes sense. And then my range, I'm going, all real numbers, negative infinity to infinity, but since we're in set builder for the first one, I'll continue in that. Cool. I feel like my teacher brackets haven't been that great on this Surface Pro here. It's an angled screen. It's a little tough sometimes. All right. For this next one, just to save time here, what I'm going to do is I'm going to work it all out. Feel free to pause the video at this time. Try graphing it on your own, dealing with that amplitude here. And then, that leading coefficient. It's actually not an amplitude with our tangent function, because it goes on forever. And then also that period change. And then hit play when you're ready to see it all worked out. And there we have it. Bingo, bango. So one thing you'll notice is that now instead of at 1, that second point is at 2. That's what the 2 out in front of the tangent did. Again, no amplitude here because it goes to infinity and to negative infinity, so it's not like there's a high and a low point. So we can't get an amplitude there. Not that it's asking for it, but I do like to point that out. Over here we got our scale when I divided the period by 4 to mark it out. I went with like a pattern method, but if you need to plug in values, you can. But I think with some practice, you're going to kind of get into that pattern mode of the behavior of a tangent function and the other ones as well. All right, we're going to do one more example in the same fashion. So feel free to pause the video and try this one on your own. I'll graph maybe like 1 or 2 periods here, and I'll put the work on the side as well. And then when you're ready, hit play, and you'll see it all up there. All right, and there we have it, folks. Our wonderful secant function, which is the reciprocal of cosine, right? So I used my cosine graph, but notice that -4 out there. That was important. I had to start down at -4 instead of up at +4 here, and then I went through my cosine progression, if you will. Over here we got how I got the period and how I got the scale. Yeah, there we go. I think we're all good here. Awesome. Wonderful. Fantastic. Feel free to pause it to take a closer look at it as I move on here, just to save some video length. Down here, we've got all of our parent functions for our reciprocals as well as tangent. So feel free to screenshot if you're that type of person, or pause it, jot them all down in your notebook. But that's all, folks. That's all. All right. America, freedom, rock and roll, Costco, Riverdog J on the gram. Have a wonderful day.